So now we're going to use an equation that you can see here that is called the combined gas law. The reason it's called the combined gas law is it combines three different gas laws that relate to pressure, volume, and temperature. But if you'd learn this one gas law, you can use it for all of the types of problems that you would use the other gas laws for. If you look on the left, you can see our variables. P is going to stand for pressure, and the units are going to be atmospheres. V is going to stand for volume, and the units could be milliliters or liters in this case. And T is going to stand for temperature, and we'll continue to use degrees Celsius for that. If we were going to read the formula out loud, I would say P1 V1 over T1 equals P2 V2 over T2. And what that means is we're going to have a pressure, a volume, and a temperature of a gas before and after. So the numbers on the left represent the initial pressure, volume, and temperature, and the numbers on the right represent the final pressure, volume, and temperature. Some of them will change, some of them may stay the same. But this equation is going to make sure that they change in the right relationship or direction. We're going to use the same tips that we've used in the past. We're going to set up the problem using the formula and use algebra to solve for the unknown information. We'll also include a photo of the work done by hand, but I'm going to do the work on the computer since many of you are using the computer for this example. So if we look at the first problem here, a rigid container is filled with 10 liters of nitrogen gas at 85 atmospheres and 19 degrees Celsius. The volume remains constant and the container is heated to 69 degrees Celsius. What will the new pressure be? So first, why don't we go ahead and highlight some of this information. So in the problem, I'm just going to highlight all the numbers that are given. We have 10 liters, we have 85 atmospheres, we have 19 degrees Celsius, and 69 degrees Celsius. I'm going to fill in what I know over here. So a rigid container is filled with 10 liters. Liters is volume, and so we're going to copy the 10 liters down here where it says initial volume. The nitrogen gas is at 85 atmospheres. So atmospheres is pressure. We're going to copy that number here next to the pressure. And then 19 degrees Celsius, and that must be the temperature. Right? It says the volume remains constant and the container is heated to 69 degrees Celsius. So 69 degrees Celsius is the final temperature. So we're missing two pieces of information, the pressure at the end and the temperature at the end. Oh my goodness, I put that in the wrong spot. We're missing two pieces of information, the pressure at the end and the volume at the end. The question is asking us what will the new pressure be, so that must be our missing information. So where is the volume? So in the second sentence, it said the volume remains constant. Constant means it stays the same. So we're going to use the same volume before and after. That means the container has not changed size. You can also say it's a rigid container because if it was a flexible container, then the container, like a balloon, for example, would change size. But it tells us in this case it's a rigid container. So picture a box or a plastic jug or something like that. Okay, we are going to replace the variables in the formula with the information that we know. So we have 85 atmospheres times 10 liters divided by the initial temperature, which is 19, equals, we don't know the final pressure, so we're going to leave the P there, times the final volume, which is still 10 liters, divided by the final temperature, which is 69. Okay. So we have an equation that we can solve using PEMDAS. We're going to do our multiplication first. So we're going to multiply the two numbers that are at the top, and we're going to get 850 divided by 19 equals P2 times 10 divided by 69. Our next step, we could divide 850 by 19. So I'm going to go ahead and do that on my calculator. I get 44.7. So now we have 44.7 equals, and we have the same stuff on the right. So I'm just going to copy and paste it. Okay. So now we have just one number on the left, but we still have a few numbers on the right. The next step is to cancel this number that's at the bottom. So the way that we can cancel it is by multiplying both sides by that amount. I'll just do this to show my step. So the number I just got, 44.7 times 69, would be 3,086.8. So I'm just going to round up to 3,087. And that's going to equal P2 times 10. And then finally, in order to get P2 by itself, we need to get rid of this 10. Since P2 and the 10 are multiplied, the way that we can cancel it is by dividing both sides by 10. So we're going to divide both sides by 10. And if I divide 3,087 by 10, I get 308.7. Equals P2, and that's going to be my answer. So I can copy that over here, but I need to make sure to add the units. So if you look at the top, the units for pressure are always going to be, there can be different units, but in our case, we're mostly going to use atmospheres, and so we're going to start with that. So in these problems, the units for pressure will always be atmospheres, and I like that one because our atmosphere, so the air around us, is naturally at a pressure of 1 atm. That's considered standard pressure. And so it does vary at different places on Earth, but that's a good number to remember. And it makes it a little easy to understand. When we say 308.7 atmospheres, that's a much greater pressure than the pressure that we have here. It's also a greater pressure than this gas started at. And that makes sense because we increased the temperature from 19 to 69 and we kept the container the same size. So it makes sense that the pressure would increase quite a bit because we're heating up a gas inside of a closed container. You can imagine if you poked a hole in that container that the gas would come rushing out because the pressure inside the container is so much greater than the pressure on the outside of the container.